Great Sitkin exploded in 2021, yet the molten rock never actually stopped rising. You expect a mountain to release its pressure and immediately settle into silence. This geological system did the exact opposite. It detonated, sent a massive column of material skyward, and then quietly shifted its entire operational behavior. Instead of emptying itself completely, the crater began receiving a continuous feed of material that is still accumulating today. Eruptions rarely maintain this kind of stubborn persistence. Most behave like a brief, forceful burst where trapped gas forces a rapid escape. Days or weeks later, the internal engine exhausts its immediate supply. Great Sitkin discarded that conventional script entirely. The explosive phase faded, replaced by an effusive phase, where lava simply pours out in a steady rhythm. That single transition fundamentally alters the level of hazard. When a volcano leaks rather than blasts, the danger moves underground. Surface conditions look entirely manageable from a distance. The mountain sits in the Aleutian Islands, a remote volcanic arc created where one massive tectonic plate slides deep beneath another. People associate that specific geography with towering ash clouds and grounded aircraft. This particular peak is doing something much stealthier. It is pushing molten rock upward, letting the gases escape slowly and stacking new material rather than shattering it. That stacking process changes the physical shape of the peak itself. Because the magma is extremely viscous, it behaves like cold honey or thick tar. It refuses to flow away like a fast-moving river. Every fresh batch of molten rock simply piles on top of the previous layer. The summit crater initially provided empty space after the 2021 explosion. Lava gradually filled that depression, overflowed the edges, and spread directly onto the volcano's outer flanks. This creates an immense, heavy structure known as a lava dome. It is not a smooth, stable architectural feature. It forms a dense, unstable pile that constantly cracks, cools, and expands from the inside out. You might assume a solidifying lid makes the mountain safer. The exact reverse is true. A growing dome represents intense geological pressure, taking a solid physical form. Underneath that enormous plug, the magma supply keeps pushing upward. Scientists from Purdue University mapped the internal structure and uncovered the reason for this relentless drive. Great Sitkin is not drawing from a single, simple underground tank. The research reveals two distinct magma reservoirs feeding the eruption. One sits deep within the crust, while the other occupies a shallower zone closer to the surface. Two interacting storage chambers severely complicate any forecast. If a mountain relies on one pocket of magma, an eruption ends when that single pocket runs dry. Connected plumbing systems completely bypass that limitation. The deeper reservoir continuously supplies the shallower one, ensuring the pathway to the surface never fully starves. They take turns dominating the flow, creating a sequential delivery system. That specific internal arrangement explains the astonishing duration of the event. The volcano functions as a highly efficient geological engine built for extreme endurance. It cycles molten rock upward as long as the connection between those two chambers remains open. This breaks the predictive models that assume eruptions must end swiftly. The Earth has found a mechanism to transport material endlessly without triggering a catastrophic release. Uninterrupted flow deposits a staggering volume of rock over months and years. The crater acts like a natural bowl, forced to accept far more material than it can ever shed. The mass thickens incrementally every single day. Observers tracking the visual feed see minor steaming and slow growth, which looks relatively harmless. Quiet surface behavior masks severe mechanical tension below. The conduit connecting the shallow reservoir to the surface acts as the critical control valve. It can become partially restricted by cooling rock or shifting structural debris. When that pathway narrows, the escaping gases suddenly find themselves trapped. Pressure begins spiking immediately beneath a lid that appears completely calm from above. This creates an incredibly precarious balance. a restricted conduit forces the entire mountain closer to the fragmentation threshold. Fragmentation occurs when confined magma abruptly shatters into airborne ash under immense pressure. The system can cross that invisible line without any obvious external warning. An effusive, slow-moving event sets up the exact physical conditions required for a sudden explosive transition. Great Sitkin already demonstrated its ability to switch operational styles. The 2021 eruption commenced with an ash-producing explosion before transitioning to lava flow. Historical records show the exact same sequence occurred during an eruption in 1974. Decades before either major event, the mountain experienced years of minor, steam-driven phreatic explosions. The ground continuously signaled that its internal structure was actively evolving. Those historical repetitions confirm that the volcano's current behavior is an established habit. A growing dome introduces an entirely separate category of severe risk. As the steep, dense pile of rock expands, its structural integrity weakens. If a major section of that dome suddenly collapses, the failure releases the trapped heat instantly. This generates swift, ground-hugging surges of scorching gas and pulverized rock. Aviation authorities monitor the situation continuously despite the lack of dramatic ash columns. The Alaska Volcano Observatory deliberately keeps the official aviation color code elevated at orange. That designation indicates active, ongoing geological unrest. Jet engines cannot tolerate any volume of volcanic ash. The microscopic particles melt rapidly inside hot turbines, sticking to internal components and thoroughly choking critical airflow. Protecting airspace requires tracking invisible signals long before the crater changes shape. Experts do not wait for a visual confirmation of an emergency. They deploy a highly sophisticated layered array of specialized instruments. Seismic sensors detect the faint, deep vibrations of rock fracturing as fresh magma forces its way upward. That underground shaking often migrates, revealing exactly how stress distributes between the two reservoirs. Satellites constantly orbit above, measuring intense thermal signatures and subtle ground deformation. The physical surface of the mountain can actually swell or sink as the pressure shifts miles below. Chemical sensors measure the specific volumes of escaping gas. Webcams provide direct visual evidence of the dome's relentless daily expansion. Each individual tool captures just a single fraction of the unfolding narrative. Combined together, these instruments reveal a massive, active plumbing system constantly adjusting its own balance. When earthquake activity spikes, analysts verify if the thermal footprint expanded simultaneously. If the physical deformation stalls, they check whether the gas output dropped. This is not simple observation. It is an ongoing, real-time interrogation of a highly complex geological structure. Most people completely ignore a volcano that fails to produce a daily spectacle. Remote locations far from major population centers easily slip from the public consciousness. Distance acts as a highly effective camouflage for persistent danger. If this exact same prolonged eruption occurred near a major metropolitan area, the continuous threat would dominate global headlines. Instead, Great Sitkin sits entirely within a massive blind spot. The human brain struggles to maintain respect for a long-duration hazard. We are deeply conditioned to react to sudden, acute emergencies. When a geological event stretches across seasons and years without drastically altering daily life, attention inevitably fades. The situation simply normalizes. People mistakenly equate a lack of dramatic television footage with a lack of significant risk. Experts view this remote isolation as an unparalleled scientific advantage. The absence of an immediate civic crisis provides a rare, undisturbed environment for intense study. Volcanologists are watching a massive, heavy-duty engine operate continuously with its protective casing completely removed. Short bursts teach scientists how mountains react under acute, temporary stress. This relentless flow reveals exactly how magmatic networks sustain themselves indefinitely. That extensive access transforms the peak into a priceless natural laboratory. Understanding how two internal chambers communicate gives researchers a crucial operational baseline. They can accurately map the precise sequence of seismic warnings that precede a shift in magma flow. They observe firsthand how a restricted conduit affects surface deformation over extended time frames. The volcano essentially shows its math every single day. These hard-won lessons possess immense practical value beyond the Eleusinian chain. Numerous other geological systems around the globe harbor similar multi-reservoir structures. Many of those highly complex systems sit directly beneath densely populated regions. The predictive patterns recognized in this isolated Alaskan laboratory will eventually travel. Recognizing an impending fragmentation event early saves lives when the mountain isn't located on an empty island. Forecasting relies entirely on distinguishing genuine precursory signals from meaningless background noise. By analyzing Great Sitkin's lengthy record, scientists refine their overall interpretation models. They learn to anticipate the subtle behavioral shifts of interacting reservoirs before the surface heavily fractures. This knowledge drastically reduces the inherent uncertainty of volcanic hazard assessments. The insights extracted from this quiet eruption sharpen the global readiness posture, yet the mountain itself remains an actively evolving problem. The steady accumulation of material never pauses for long. Every newly hardened layer of rock adds immense weight and alters the internal stress distribution. The physical dimensions of the crater continuously adapt to the incoming supply. The central vent geometry changes slightly with every single cooling pulse. The initial explosion in 2021 was not a sudden, isolated shock. It followed a distinct period of buildup characterized by elevated heat output and abnormal gas emissions. These specific markers indicated that the vast underground architecture was actively pressurizing. The subsequent blast simply cleared the immediate throat of the volcano. It acted as a massive transition phase rather than the actual main event. You might assume that releasing that immense pressure would fundamentally deplete the mountain's energy. That is the exact trap most observers fall into. Because the gas successfully escaped during the explosive phase, the remaining molten rock faced far less internal resistance. It transitioned into a smooth, effusive crawl. This incredibly slow movement drastically masks the true volume of the displacement. Consider the sheer scale of this ongoing geological transfer. The Earth is steadily moving countless tons of deep crust material directly onto the surface. This isn't an abstract scientific concept. It is physical landmass being constructed in real time. The crater essentially acts as a highly efficient manufacturing facility. It transforms extreme subterranean heat into a permanent hardened footprint on the map. The viscosity of the lava dictates the shape of that new footprint. If the magma were highly fluid, it would rapidly drain down the steep flanks and disperse. Because it resembles thick, resistant tar, it forcefully stacks upon itself. This unique physical property directly enables the crater to function as a storage container rather than a mere funnel. The resulting dome expands outward only after the center becomes completely overwhelmed. This continuous piling heavily stresses the surrounding bedrock. The intense thermal contrast between the scorching interior of the dome and the freezing Alaskan air creates deep structural fractures. These new cracks constantly alter how subsequent batches of magma navigate the final approach. Every single fracture acts as a potential new pathway or a dangerous new blockage. The mountain literally rewires its own internal plumbing on a weekly basis. Such dynamic internal shifting renders long-term prediction exceptionally difficult. A rigid, unchanging system behaves predictably. Great Sitkin presents a constantly moving target. When the shallow reservoir temporarily exhausts its local supply, the deeper chamber immediately compensates. This seamless handoff prevents the eruption from naturally choking off. It guarantees that the baseline threat level never fully drops back to zero. This relentless continuity severely tests the endurance of the monitoring grid. The Alaska Volcano Observatory must maintain absolute vigilance across multiple overlapping sensor networks. They rely on satellite telemetry to pierce the heavy cloud cover typical of the Aleutians. These orbital assets measure the precise expansion rate of the dome in millimeters. A sudden spike in the growth rate could precede a major structural failure. Simultaneously, the seismic arrays map the invisible depth of the tremors. A low-frequency rumble indicates smooth fluid movement. Sharp high-frequency cracks signal solid rock forcefully snapping under extreme pressure. By continuously cross-referencing these unique auditory signatures, analysts can literally hear the magma rising through the dual reservoirs. They build a three-dimensional model of the hidden threat. This highly complex operation proves that an eruption does not need to generate cinematic footage to remain highly consequential. The local aviation corridors heavily depend on these precise daily assessments. International cargo flights traversing the northern Pacific Rim require immediate alerts if the fragmentation threshold is crossed. A seemingly calm, dome-building phase can instantly revert to an ash-spewing hazard if the internal conduit suddenly seals. The true value of Great Sitkin lies entirely in its stubborn refusal to conform to expectations. It forces observers to abandon simplistic, cartoonish models of underground magma chambers. The Earth operates through highly integrated, multi-layered networks. When one branch slows, another forcefully compensates. This profound realization completely changes how geologists evaluate unrest at other global hotspots. Every additional month of this continuous flow adds critical data to the scientific playbook. Researchers can conclusively map how a stable plateau of activity eventually destabilizes. They learn to precisely differentiate between a temporary pause and a permanent shutdown. This vital distinction often determines whether evacuation orders in populated regions are issued or lifted. The remote Aleutian Peak serves as an irreplaceable training ground for high-stakes forecasting. The concept of duration fundamentally reshapes how human beings perceive geological risk. We are programmed to measure danger through immediate intensity. A sudden, short-lived blast commands instant respect and triggers immediate emergency protocols. A drawn-out, effusive event invites a dangerous sense of complacency. The slow accumulation of thousands of tons of heavy rock simply does not register as an urgent crisis, yet this extended time frame multiplies the ultimate consequences. The massive volume of material transferred over several years vastly exceeds the output of many sudden explosions. The physical footprint of the mountain expands relentlessly, new ridges form, deep valleys fill, and the entire local topography undergoes a profound, permanent transformation. The Earth accomplishes through sheer patience what it normally achieves through sudden force. This requires an entirely different methodology for evaluating the hazard level. You are no longer waiting for a singular event to pass. You are managing an ongoing, highly volatile condition. The primary threat shifts from the sky directly to the ground. Instead of tracking airborne ash clouds, analysts must calculate the maximum load-bearing capacity of the expanding dome. When a dome exceeds its structural limits, the resulting failure is severely swift. Gravity takes over, pulling massive sections of the fractured rock face downward. This depressurization instantly vaporizes the trapped gases within the rock matrix. The resulting surge of superheated material races horizontally across the terrain, conforming to the existing valleys and leveling any obstacles. It represents an entirely different class of extreme hazard. This creates an incredibly tense and unanswered geological question. A connected plumbing system will persistently push molten rock upward as long as the deep source provides it. The container at the summit fills, expands, and completely restructures its own boundaries. The outside world looks away, assuming the long event will eventually taper off harmlessly. But the dual reservoirs below show absolutely zero signs of shutting down. When a highly pressurized system keeps receiving massive inputs, it eventually reaches a structural limit. The lava continues to rise, stack, and forcefully spread outward today. The heavy dome sits like a massive, unstable cap over an open, active pipeline. You only have to wonder what the final surface will look like when the mountain simply runs out of room.